Meena Shaheen, and today my topic of discussion is alloy formation in aluminium, nickel, manganese, and iron. Today I will presenting my assignment. So first of all, I will tell you about metals. Metals are rarely used in their pure form because pure metals often lack sufficient strength, corrosion resistance, or thermal stability. To overcome these limitations, alloy formation is used. Alloying involves adding one or more elements to a base metal to modify its structure and properties. Aluminium, iron, nickel, and manganese are among the most important engineering metals. Iron forms the backbone of steel. Aluminium provides lightweight strength. Nickel contributes high temperature and corrosion resistance, and manganese plays a critical role in phase stabilization and grain refinement. In this presentation, I will first explain the basic chemistry of these metals, then discuss the material science mechanism of alloy strengthening, followed by synthesis routes, AI and machine learning applications, engineering and biomedical uses, and finally future perspective. Let us begin with iron. Iron is a unique metal because it shows allotropic phase transformation. At room temperature, iron exists as alpha iron or ferrite, which has a body-centered cubic structure. When heated above 9-10 degrees Celsius, it transforms into gamma iron or austenite with a face-centered cubic structure. This phase transformation is extremely important in steel processing, allowing elements such as nickel and manganese stabilize the austenite phase, meaning they allow the face-centered cubic structure to exist at lower temperature. Iron also contains partially filled 3D orbitals which make it magnetically active. When alloyed, these electronic interactions change affecting mechanical strength, toughness, and magnetic properties. In short, iron's phase flexibility allows engineers to control microstructure using heat treatment and alloying. Now let's talk about manganese. Manganese is widely used in steel making as an austenite stabilizer and deoxidizer. It removes oxygen and sulfur impurities and improves steel cleanliness. Manganese also delays the transformation from austenite to ferrite, allowing deeper hardening during quenching. High manganese steels such as hard head filled steel show exceptional wear resistance and work hardening. In aluminium alloys, manganese behaves differently. It has low solubility as it forms intermetallic dispersoids instead of precipitates. These dispersoids spin grain boundaries and prevent recrystallization, improving thermal stability. Next is nickel. Nickel has a face-centered cubic structure and strongly stabilizes face-centered cubic phases in alloys. In steels, nickel improves toughness and corrosion resistance, especially at low temperatures. In nickel-based superalloys, nickel forms the matrix phase known as gamma. Strengthening occurs through the formation of gamma prime precipitates, usually nickel aluminium. These coherent precipitates block dislocation moment even at very high temperature. That is why nickel alloys are used in turbine engines and aerospace applications. Now let us discuss about aluminium. Aluminium is lightweight metal with excellent corrosion resistance due to its natural oxide layer. However, pure aluminium is soft, so alloying is essential. Different alloying elements serve different purposes. Magnesium provides solid solution strengthening. Copper and silicon enable precipitation hardening. Manganese forms dispersides that improve thermal stability. In precipitation, hardened aluminium alloys heat treatment produces fine intermetallic particles that strongly resist dislocation motion. This balance of low density and high strength makes aluminium alloys ideal for transportation and airspace structures. Now I will discuss about the key strengthening mechanism. Alloy strengthening and stabilization arise from several key mechanisms which often operate simultaneously in practical alloys. First of all, I will talk about the solid solution strengthening. When alloying atoms dissolve in the host metal lattice, they create local lattice distortions due to size and modulus mismatch. These strain fields interact with stress field of solute atoms. Substitutional solutes, nickel in iron or copper in aluminium, and interstitial solutes, for example carbon in iron, both produce this effect. The classic description notes that the local non-uniformity in the lattice due to the alloying element impedes dislocation motion through stress fields. In practice, alloying iron with a few percent nickel or manganese or aluminium with magnesium silicon raises yield strength via this mechanism. In high entropy alloys, vast solid solution strengthening occurs because of extreme lattice distortion from multiple principal elements, as you can see in this figure. Number 2 is precipitation hardening. Here alloys are purposely aged to form a second phase of fine particles within the matrix. For example, quenching an aluminium copper or aluminium magnesium silicon alloy from high temperature creates a supersaturated solid solution. Subsequent aging precipitates intermetallic compounds aluminium, copper, magnesium, silicon as nanoscale coherently strained particles. These impede dislocations more strongly than random solute atoms. In nickel-based superalloys, the gamma phase nickel aluminium or nickel titanium aluminium precipitates coherently with the gamma matrix. As stated in a classic definition, precipitation hardening produces fine particles of an impurity phase which impede the movement of dislocation. When these precipitates remain coherent, lattice matched with the host, they exert strong coherency strengthening. Dislocation must cut through or bypass these particles in nickel superalloys. For instance, the ordered lithium nickel aluminum structure shears by forming complex stacking fault configurations, greatly raising strength. The overall effect is a large increase in yield strength, especially after optimal aging. Next is phase transformations. Alloying enables control over solid state phase changes. In steel, diffusion control transformations, austenite to ferrite, pearlite on slow cooling, or austenite to benite on moderate cooling, form microstructures balancing strength and toughness. On rapid cooling, a diffusionless martinistic transformation occurs. Phase center cubic gamma iron transforms to a distorted body center tetragonal BCT. Martensite that is supersaturated in carbon. This martensite is extremely hard because it is strained and maintains excess carbon in solid solution, yielding additional solid solution strengthening. The martinistic phase generates an increase in hardness because the dislocation cannot easily move through the supersaturated distorted lattice. Thus, by adjusting alloy chemistry, for example carbon and manganese content and heat treatment, engineers can tailor steel microstructures for desired combination of strength and ductility. In non-ferrous alloys, phase transformations like age hardening precipitate sequences. For example, aluminium lithium gamma phase transformation also fall under this category of diffusion mediated microstructural control. As you can see in this flow sheet diagram, diffusionless phase transformation, how it is proceed? It will proceed through two energies, interfacial energy and strain energy. Interfacial energy corresponds to the shuffle transformations, which means kinetics and morphology dominated by shuffles. And strain energy is linked with the lattice distortive transformations. It means kinetics and morphology dominated by lattice distortion. There are two types of component, dilational components and deviatory component. Dilation dominant means no undistorted line. Deviatory dominant means undistorted line. Undistorted line has two components, atom vibrational displacement and lattice distortive displacement. Atom vibrational displacement has quasi-martinistic and lattice distortive displacement has martinistics. Quasi-martinistic approach has kinetics and morphology not dominated by strain energy, and martinistic approach means kinetics and morphology dominated by strain energy. Now let's talk about the number 4 mechanism, that is grain boundary engineering. Grain boundaries act as barriers to dislocation motion. The Hall-Petch relationship quantifies this as grain size decreases, yield strength increases roughly. As you can see this equation, in polycrystals, dislocations pile up at boundaries. Smaller grains mean less pile up and higher applied stress needed to transmit slip, thus alloying and processing that refined grains through controlled solidification or thermomechanical treatments directly boosts strength. Moreover, special boundary engineering via deformation and annealing increases the fraction of low energy. Coincidence site lattice CSL grain boundaries in alloys. A higher proportion of these special boundaries significantly enhances resistance to intergranular failure modes, that is corrosion, creep, and fatigue. For instance, increasing the fraction of sum of three twin boundaries in nickel-based alloys or steel has been shown to improve creep and fatigue life. In summary, by manipulating grain size and boundary character through alloy addition and heat treatment, one strengthens the material and improves creep fatigue resistance. As you can see on this diagram, grain boundary engineering Hall-Petch relationship, as you can see, the variation of grain size with the yield strength in first diagram, then grain refinement and coincidence site lattice CSL grain boundaries. Grain refinement is linked with the grain refinement coincidence site lattice CSL grain boundaries. As you can see, smaller grain size means higher strength and toughness. More CSL boundaries means improved creep and fatigue resistance. Alloy properties depend strongly on processing method. Now I will talk about the synthesis of alloy formation. Alloy microstructures depend critically on how the alloy is produced and processed. First method is casting. Casting means first melting and then solidifying is the traditional method. During solidification, cooling rate and the thermal gradients determine segregation, then dried structure and grain size. Rapid cooling, for example in die casting or additive manufacturing, can trap solute micro segregation and produce fine microstructure, while slow cooling allows more diffusion and coarse grain. Control of cooling is essential. For example, homogenization heat treatments after casting promote diffusion of solutes to reduce segregation. Stirring or electromagnetic processing of the melt can also improve homogeneity. The second method is thermomechanical processing, that is forging, rolling, extrusion. Heat and deformation are combined to break up cast structures, refine grains, and induce work hardening or dynamic recrystallization. The interplay of deformation, temperature, and strain rate controls recovery and recrystallization and thus final grain size. Next method is powder metallurgy. Powder metallurgy produces fine and uniform microstructures with minimal segregation. Powder metallurgy offers another path. Metal powders are blended mechanically, alloyed if needed, compacted, and sintered. This allows near net shaping and can yield very uniform alloy composition with fewer macro segregation issues than casting. Techniques like spark plasma, sintering, or hot isostatic pressing facilitate diffusion bonding. PM routes can achieve fine uniform microstructure and are used for alloys that are difficult to cast or require special chemistries. The next one is additive manufacturing. Additive manufacturing uses extremely rapid cooling, creating non equilibrium microstructures. Additive manufacturing, notably laser powder bed fusion, LPBF, and directed energy deposition, builds parts layer by layer. Additive manufacturing induces extremely high cooling rates, 10 raised per 3 to 10 raised per 6 kilo per second, resulting in non-equilibrium microstructure. For example, supersaturated solid solution, metastable phases, or very fine cell structures, as a recent study shows, pronounced microsegregation in as a printed alloys can strongly affect subsequent recrystallization behavior. By tuning scan speed, laser power, and layer orientation, AM can program localized microstructure. For example, site-specific thermal histories allows some regions to recrystallize while other remains in a rod-like state. Overall, AM is revolutionizing alloy synthesis by enabling complex geometries and gradient microstructures that were unattainable by conventional casting or forging, also controlling defects. Porosity and isotropy remains a challenge. Across all methods, diffusion kinetics and solidification pathways are key. Controlling the partition coefficient and thermal gradient during solidification mitigates solute segregation. Post solidification heat treatment like solution treatment plus aging exploit diffusion to equilibrate composition and precipitates hardening phases. Thus, whether by casting, powder, routes, or AM, the processing condition determines phase formation and grain structures, enable the design of alloys with specific properties. Now, let's talk about the AI and machine learning in alloy design. Modern alloy development increasingly uses artificial intelligence and machine learning. Machine learning models can predict phase stability, mechanical properties, heat treatment, response. Recent years have seen the rise of data driven material design. Material informatics combine large databases with machine learning to predict alloy behavior. For example, machine learning models, neural networks, random forest, etc., trained on non alloy data can estimate phase stability and yield strength as functions of composition and heat treatment conditions. In particular, integrating machine learning with caliphate calculation of phase diagram thermodynamics has shown great promise. A recent study demonstrated that machine learned interatomic potentials like M3GNet or ORB can be used within a caliphate framework to compute phase diagram orders of magnitude faster than density functional theory with comparable accuracy. This enables rapid screening of multi-component alloys including high entropy systems that would be prohibitive by experiment or pure computation alone. More broadly, AI tools in metallurgy predict optimal alloy compositions and heat treatment recipes. For instance, supervised machine learning can identify which elemental ratios yield a desired phase friction, while unsupervised learning can classify microstructure images, generative models, for example, Bayesian optimization, help explore vast compositional spaces to suggest novel alloy chemistries. The synergy of machine learning with traditional approaches like experimental design, high throughput synthesis, and caliphate models is accelerating discovery. As one review notes, data driven surrogate models now enable predictions based on past data rather than on solving fundamental equations, which is particularly useful when experiments are costly. In some, AI machine learning integration is transforming alloy design into an interactive high throughput process. Phase diagrams can be predicted on demand and candidate alloys optimized computationally before ever making a sample. Now talk about the engineering and medical application. Alloys of aluminium, nickel, manganese and iron underpin many critical applications. Number 1 is aerospace turbine engines. Nickel-based superalloys, for example, iconal ring alloys with gamma-gamma microstructure retain high strength and creep resistance at 700 to 1100 degrees Celsius. These are used for turbine blades, disc, and combustor parts. The coherent nickel aluminum type precipitates in nickel alloy provide excellent high temperature strength. Innovations in gamma chemistry, along with titanium, helium, etc., have extended their operating temperatures and lifetimes. Nickel alloys are also used in space and marine applications for similar reasons oxidation resistance strength. Number 2 is lightweight transportation. Aluminium alloys, especially aluminium magnesium silicon and aluminium lithium types, dominate automotive and aerospace structures to reduce weight and improve fuel economy. DOE analyses indicate a 10% mass reduction yields 6 to 8% fuel saving. Modern cars use AI panels, engine blocks, and suspension components. Airplanes use AI, copper, and aluminium lithium alloys in fuselage and wings. These alloys combine low density with precipitation hardening to reach strengths near those of steel while cutting weight. As noted by Energy Efficiency Program, replacing steel with aluminium can cut component mass by up to 50%, directly boosting vehicle efficiency. The next application is nuclear application. Iron, nickel, chromium alloys, stainless steel, and emerging iron nickel based high entropy alloys are key in reactors. Austenitic stainless steel, iron, nickel, chromium are used for reactor internal and piping due to good radiation resistance. Recent research on iron, manganese, chromium, nickel, high entropy alloys has shown even better radiation tolerance. For example, chromium, iron, manganese, nickel alloy exhibited fewer irradiation induced defects than standard SS under high dose proton exposure, suggesting superior performance under reactor conditions. Thus, iron nickel based alloys continue to be tailored for harsh nuclear environments, high temperature neutron flux. The next one is, and the most important application is biomedical implants. Metallic biomaterials for temporary implants benefits from alloying. Traditional stainless steel and titanium alloys are common, but interest in biodegradable metal is growing. Iron manganese alloys, sometimes with additional silicon or carbon, have been developed as biodegradable implant material. They corrode slowly in the body without any harm, and there is no need of second surgery to remove these metals from the body, and they have good strength. For example, an iron 29 manganese 5 silicon shaped memory alloy after severe plastic deformation showed biocompatibility as well as high strength and low elastic modulus, ideal for orthopedic fixation devices. Such iron manganese X alloys can provide initial load bearing support and then dissolve safely, eliminating the need for removal surgery. Early studies report that iron manganese alloys have acceptable biocompatibility in vitro and in vivo, supporting their potential use in degradable implants. To conclude, alloy formation in aluminium, iron, nickel, and manganese is central to modern material engineering. Future research will focus on sustainable alloy design, recycling friendly composition, high entropy alloys, AI driven discovery. Looking ahead, alloy development will emphasize sustainability and multifunctionality. Sustainable alloying involves greater use of recycled material and low carbon production method. For instance, recycling aluminium saves 95% of energy versus primary smelting, dramatically reducing emission. New solid state recycling and extrusion methods, for example, hot extruded AI scrap, can tune alloy properties while lowering environmental impact. Lightweight via aluminium and corrosion resistant iron nickel alloys continue to reduce fuel use and maintenance burden in transportation and infrastructure. Next is multifunctional material are also a frontier combining high strength with other functions, shape, memory, magneto-resistance, bioactivity. Could open new uses. For example, aluminium, manganese, silicon iron alloys already act as a dispersoid strengthened grade for high temperature use and nickel, manganese, gallium, ferromagnetic shape memory alloys. Although outside or element sets show the type of multifunctionality possible, magneto-structural, Hustler, and eutectic system containing these metals may yield alloys for sensor, actuator, or energy harvesting. High entropy alloys and complex concentrated alloys involving iron, nickel, manganese, and aluminium are an active area. Equiatomic or near equiatomic aluminium, chromium, iron, manganese, nickel, and derivatives form novel microstructures with promising high temperature strength and stability. For example, aluminium, cobalt, chromium, iron, nickel, titanium, high entropy alloys have shown outstanding elevated temperature performance. Iron, nickel, manganese, aluminium, high entropy alloys may yield a balance of low density from aluminium and creep strength from nickel and chromium for aerospace. Although research is still emerging, in general, high entropy alloys offer a vast new design space by combining multiple alloying effects. Finally, AI accelerated discovery will become standard closed loop platform that integrate machine learning with high throughput experiments and CalFed will greatly compress development time. For instance, machine learning guided interaction can quickly home in an optimal composition for a target application. For example, maximizing yield strength subject to a density constraint. Far faster than trial and error, as demonstrated, machine learning potential can generate CalFed compatible thermodynamics for multi component systems within a high throughput framework. Pointing toward on demand phase diagram generation, we expect more tools that predict properties, hardness, ductility, corrosion traits from composition and process parameters validated by robotics driven experiments. In summary, the alloying of aluminium, nickel, manganese, and iron remains a rich interdisciplinary field. Future research will not only refine classical alloy system but explore new compositions, for example, lithium or high entropic additions, and leverage AI to discover sustainable multifunctional materials that meet the demands of energy efficient, high performance technology. Now, if we talk about the abstract, that is, alloy formation is a cornerstone of material science, enabling the tailoring of mechanical, chemical, and functional properties for beyond those of pure metals. Aluminium, nickel, manganese, and iron, four abundant and technological critical elements, serve as primary components in many advanced alloys. This review traces the underlying chemistry of the elements, for example, iron's body center to face centered polymorphism, manganese's role as an austenite stabilizer, nickel's face centered cubic stabilizing effect and corrosion resistance, and aluminium's low density and passive oxide surface, and examines how their electronic structures and bonding characteristics dictate alloy behavior. Key strengthening mechanisms are discussed: solid solution strengthening, where size mismatched atoms create lattice strains that impede dislocation; Precipitation hardening means in which controlled heat treatment yield finely dispersed coherent particles. Phase transformation including diffusion driven transformation. Grain boundary engineering where grain refinement and special boundary control enhance yield strength and creep fatigue resistance. And we had discussed the different synthesis method. Then we had discussed the artificial intelligence and machine learning. So this is all about my topic, and the keyword of the topic is aluminum alloy, nickel based superalloys, iron alloys, manganese alloying strengthening mechanism, machine learning and material science. Thank you so much.